All right, so the first thing we're going to talk about is variance. So we're going to start with a motivating example by defining some new types. One int a. T1, T2, G. A int. T2, T3G, and this one is A to A. So yeah, we're going to define these new types, and then we're going to define variance, and then we're going to use variance to figure out which one of these have functor instances, basically. So you can tell just by looking at the types which one of these is a functor instance, which is pretty crazy to me. And I never knew you could do this, so it's exciting. So int to a to int I have 4, and then a to int, I believe. Yes. Okay, so here are the new types, and then we'll discuss variance. I should make sure I'm not dropping. Oh, good. So variance. I wrote this in my notes, so we'll start with the definitions. So you can have covariance, which says that a function a to b can be lifted into ta to tb. So if you have a decent eye, you will notice that this is basically fmap. Contravariance is a to b can be lifted into tb to ta. So the opposite of covariant. And then you can have invariant, cannot be lifted into D. Let me use the no function. Let's use no function a to b can be lifted into a function containing ta. Right, because it could be either in the left or right position of the arrow. No function can be lifted into a function containing t of a. Okay. So there apparently are packages on Stack for both contravariance and invariance. So what I would like to do is, when we figure out which ones are functors or not, we can try and implement contravariant, whatever function there is for contravariance. It's Haskell. Theta functor contravariant. Okay. Haskell 98 contravariant functors. That's what we're looking for. But how do we use them? Here. Compose? I don't think I want to compose. Probably generic. Don't think so. Visible. Is there not just a contravariant type? Everything's in terms of this divisible thing. Divisible contravariant functor, the monoid object, the category of pre-sheaves. This doesn't mean anything to me. Okay, so it doesn't look like it's super convenient to implement this, although maybe that's the point. I'm not really sure, but that's fine. I know there's also an invariant function or invariant package. Invariant map. That's funny. That's interesting. We're not going to try to implement these, I guess. Maybe we will. Maybe we'll implement the other ones. Okay, so that's the definition of variance. And then there's basically like a, Sandy put map in the book, but there's no, apparently no oh yeah, here it is. Contra map. But I didn't see it. Why didn't I see it? Try and find it, because I'm contra. Defunctor contravariant. Was I looking at the wrong thing? I must have been looking at the wrong thing. Okay, maybe we can do this. I don't really know how, but we'll keep those. Maybe we'll do it. Okay, so apparently you can tell whether something is covariant with respect to its with respect to a variable via a pretty simple table. So let me put this table out here. Do it this way. And then okay. So obviously we're gonna have to move this over because we don't really have a typesetting thing here. So A is in a plus position, B is in a plus position, plus position. I'll explain what these positions mean here in a second. This is No one is on again. I don't know if that's because no one is actually here or because Moobot is not working again. Okay. And then let's put a like this. All right, so basically what you can do is if you put these things together and you get a positive value, that ends up being covariant. If you put these things together and you get negative, that's contravariant. And if you get that they're plus and minus with respect to both, then they are invariant. So let's just take the examples above, and actually we'll put these down here and we'll document them. Okay, so with respect to A, this is on the right side of the arrow, so it's plus. Just put like some space over here, so it's covariant. Variant, I suppose. Here, this is a minus position, which means this is contravariant. This one is in a minus and a plus position, which means it's invariant. This one is in a plus position here, right? But it's also in a minus position. So so I'm gonna say, how do I write this in here? What if I do this? He has a nicer way of printing this, but so I'm gonna put some dashes here to try and show that it's this whole thing. That's kind of okay. Right, so basically this means you multiply these together, or that's the way you think about it. So in this case, you're not multiplying them. You're saying that these are in both positions. So if it's in both positions or plus minus, then you do this. But if they're it's in two positions at once, then you're multiplying these together. So this ends up being minus, which is contravariant. Right, and then this one is kind of like this, but this time it's plus, sorry, it's still minus, but it's also minus here, right? So this becomes covariant. Variant. And then let's in, how do we say this? Covariant in A, I believe. I think that's the right way to say that, in A. Hello, single viewer. Hope you're having a good day. We are discussing covariance and contravariance and invariance, which is like a really quick way to decide if something has a functor instance. So we were basically given these new types, and we have to decide which one of these has a functor instance or not. And just by knowing its variance, you can know if it has a functor instance. So basically, you just look at the type with respect to whatever variable you're interested in, and you can just figure out its variance using this position chart and decide if something is covariant, contravariant, or invariant. So in this case, if you look over here, the B is a positive position. So you assign this a positive position, and if it is a positive position, you end up with a covariant type. In this case, it's a negative. So if you just, again, you just look at the table, it's on the left of the arrow. So it's contravariant, and therefore, it's negative and therefore contravariant. In this case, you have them in both positions, which means it's invariant. In this case, it's a little trickier because it's in one position of two values. So if you when it's this way, you have to multiply both the positions together, and you can think of it like 1 and -1. If you multiply them, you get -1. If it's plus and plus, you get plus. If it's minus minus, you get plus. So that's basically what we have here. We have A is in a minus position because it's on the left of the arrow, but it's also on the right of the arrow inside here. So it's plus minus, and therefore it's minus contravariant. Minus minus, you multiply those together, same thing, we just flip this around. That becomes covariant A, which means that T1 has a functor instance, so we can just write it. We know it exists, so we can just write it. F to T1A T1 fx. Wait. No. It's F. This is an F. So I think you compose them. This takes an int to an A. This takes an A to a B. Is this not right? Oh, duh. I changed the name. There you go. So you can just compose them, and in this case, it's really just, you can just write fmap. It's the same thing. I don't know what's more clear. I mean, they're literally the same thing in this case, because functions have a functor instance, and their functor instance is just to compose them. Okay. So what I want to try is see if I can write the contramap instance of this. But first we got to get contramap. I don't know if I can do it, but I'll try. We need package YAML, and we need a dependency of contramap. No. Covariant. Is that what it's? Contravariant. I keep writing covariant. Contra. So if we write that, and then we import data functor contravariant. Okay. And then in theory, we can write an instance for it. Contravariant T2 where contramap, and it's going to be F T2 yeah, just got to be the other way, right? Interesting. Okay, and then for the next one, we also need another package called invariant. And then we can import functor in, whoops. And then, so wait, does that imply that contravariant is included? I feel like I read something that one of these was, I thought it was bifunctor though. Oh, I see. Okay, I'm writing this wrong, so let me correct this. A is covariant in TA. That's the A is contravariant in TA. Well, T1A, right? 2A. A is invariant in 3A. And A is contravariant in T4A. Finally, A is covariant in T5A. Okay, I think that's the correct way to write that. So the next thing, hopefully my head isn't in the way of those, but it might be. Scroll down. So now we should be able to write an instance of invariant T3 where inv map. So this takes a fab, an FBA, and a T3 of A. So T3 that's interesting. Would this have been helpful when we were making our isomorphism checks? This invariant in map thing? I guess not. Because you still need FAB and FBA. Anyway, okay, so next one. is going to be an instance of contravariant T4 where contramap these are probably terrible names, but trying to help myself under or think about them. Oh, restart GHC. Isn't that what it was? Invariant. Invariant. Still not working. Seems fine now. Types aren't coming in. Oh. Wake up. Seems broken. Why is it not doing anything? Doesn't seem to have failed. Oh, maybe I think I know what I do. So because we probably have to build transformers. T5. But if you watch them on Twitch now, you'll be able to see them. So this is F. Sorry, I guess. Okay, so there are the two stubs, and then uh-oh, we failed. Okay, so anyway, we should in theory have type checking in here now. Okay, let's oh wait, no, we're not going to because we have this error. So let's this, oh, here we go. Okay, so this is an A, this is A to B, B to A, but we need to end up with T3 of B.